Hello students, let us take a simple case of motion in a straight line, which is also called the one-dimensional motion. Motion along a straight line is called one-dimensional motion. If you have motion in a plane is two-dimensional, both x and y directions are there, so that will be called two-dimensional motion. Now, if we are discussing motion in a straight line, first of all, we don't have to use an arrowhead over the quantity. It is not essential. I can write v as dx by dt if the motion is along x direction. Now, because if a particle is moving along a straight line, then there are only two possibilities for direction. Velocity of the particle may be either towards right or towards left. If we take one of the direction as positive, if I am taking right as positive, then if the velocity is towards left, it will be indicated as negative. So positive value of v will mean x is increasing. That means the particle is going towards right. A negative value of v will indicate the particle is moving towards left. The value of x is decreasing. And for acceleration, again, we are not using arrow here. We can simply denote the direction by sign. Positive acceleration will mean the rate of change in velocity is towards right. Negative will mean the rate of change in velocity is towards left. So we don't have to put arrow signs here to denote the vector quantities if we are discussing a one-dimensional case. Now, let us take an even easier sub-case of this one-dimensional motion. The motion in a straight line with uniform acceleration. Suppose a particle moves at a constant acceleration a. At t equal to 0, the particle is at origin and it is moving with velocity u towards right. After some time t, it is at this position and it is moving with velocity v. So how do we relate this? The basic relation we will use is this one, a is equal to dv by dt. Now, from this, I can say that dv is equal to a dt, and I can integrate the two sides over this interval to get the relation. Now, as time changes from 0 to t, the value of velocity changes from u to v. We can also express this relation with the graph. I can draw the velocity time graph. The graph will be a straight line because the velocity is changing at a constant rate. If the rate of change is constant, you can expect a constant slope of the graph. Now, at the initial moment, the value of velocity is u, and after some time t, it becomes v. All right. So, if we do the integral of 1 will simply be v, and we have to put the limits u to v. A is a constant. Integral of 1 will be again t, and we have to put limits 0 to t. Left hand side will become v minus u. Right hand side is a into t. So you get the relation v is equal to u plus at. Remember, this equation is valid only if the particle is moving with uniform acceleration, whereas this result will be valid even if the acceleration is changing. So this is our first equation of motion. You must be familiar with this. V is equal to u plus at. If s is the displacement of the particle, we can see that for a small time duration dt, displacement will be given by this very thin area here ds, and by integrating this, which means the total area under the velocity time graph, we will get the displacement. So I replace v here by ds by dt. So v, which is ds by dt, velocity is rate of change in displacement, can be written as, we know this is u plus at, and then we can separate the variables here. Integral of ds will be, we can take dt on the other side, u dt integral plus at dt integral. Limit for time 0 to t, and for s 0 to s. So this becomes s is equal to ut plus half at square, which is the second equation of motion. First one gives us the velocity as a function of time. Second one tells us the displacement as a function of time. There is a third equation of motion you must be familiar with. You can get that equation by eliminating t between these two. That means putting the value of t from here to this equation and then solving, you can get the third equation of motion, which is of course v square equal to u square plus 2as. But there is another way of directly deriving this third equation of motion. In that direct method, what we do is we write acceleration in terms of v and s. So what we can do is we can write acceleration, which is dv by dt, using chain rule. This can be written as dv by ds multiplied by ds by dt, and of course ds by dt is v, so it becomes v dv by ds. You are already familiar with this application of chain rule. So we can separate the variables. We can say v dv is equal to integral v dv is equal to integral of a ds. Displacement changes from 0 to s, velocity changes from u to v, and after doing this integral, you can say that the left hand side will be v square minus u square by 2, whereas the right hand side is as, and simplifying this you will get the third equation of motion. So these are the three equations of motion you must have studied in your class 9th or 10th, and they are very helpful in solving the problems of motion in one dimension, motion in a straight line with uniform acceleration. If you notice, there are total 5 symbols being used here: S, U, T, A and V. These are the 5 symbols. Now out of this, acceleration is a constant. The other 4 are, acceleration is a constant, and also initial velocity u is a constant because it's the value of velocity at a particular moment, at a given moment t equal to 0. So these are constants. The other things, namely s and v, these are function of time. They change as time changes. So one more thing, out of these 5, how many are vectors? 4 of them are vectors except for time here. All others are vectors. Initial velocity is a vector. Final velocity is a vector. Acceleration we know is a vector. S here we must remember is displacement. It is not distance traveled, it is displacement. So that is also a vector. I had to mention this, that these are vectors, because we are not using arrows over them. Alright. Now in a straight line motion, only 2 directions are possible. If it is say horizontal line, if right is positive, left is negative. So positive or negative values of these vector quantities is basically giving their direction. Remember, magnitude of a vector is never negative. The sign is only indicating direction. In each of these three equations, one of the quantities is missing. In equation 1, we don't have S. In equation 2, V is missing. In the third equation, time is missing. Derive an equation in which A is missing. That means get a relation for displacement in terms of U, V and T. You can do this by using this graph. See, what is displacement? Displacement, we can say in terms of graph, it is the total area under the VT graph. Total area under the velocity time graph will give you the displacement. We already found this thin area ds, thin area equal to ds. So the total area will give you the total displacement S. Now this area is in the form of a trapezium. Area of a trapezium, you can write this as half of the sum of parallel sides, which are U and V. So half of U plus V multiplied by the distance between the parallel sides, which is T. So this is the required relation for S in terms of U, V and T. You can get this relation also by eliminating A between these two equations. That means you can get the value of A from equation 1 and put it here. That will also give you this relation. Let us take an example based on our three equations of motion. Particle is moving with initial velocity 2 meter per second and acceleration 1 meter per second square, both directed towards right. We have to find these three things: displacement, distance traveled in 4 seconds, time at which velocity is 7 meter per second, and velocity when displacement is 6 meters. Now, first of all, we should think of the signs of these quantities. See, the sign of a vector quantity will be decided by its direction. Question says both U and A are towards right. So, if we choose right as our positive direction, U and A are both positive. Alright. Now, come to the first part. Which of the three equations should we use for the first part? See, it depends on what is given in the question and what has been asked. U and A are given and we have to find distance traveled. Although distance traveled doesn't come in any of these equations, but we can surely find the displacement. So, let's find displacement at 4 seconds, then we will think about the distance. So, this is the equation which connects displacement to U, A and given T. So, we will use equation number 2 for first part. This will give us S is equal to U is 2, time is 4 plus half, acceleration is 1, T squared is 4 squared. You can solve this. This is 8 plus 16 by 2, again 8. So it is 16 meter. So this is the displacement of the particle in 4 seconds. But question asks about distance traveled. Now in this situation, particle is moving along a straight line and secondly, it hasn't turned back. We can be sure that it hasn't turned back. Even in a straight line motion, see, distance and displacement can be different. If the particle goes straight and then it turns and come back, in such a scenario, distance, displacement, they can be different. But here, there is no question of its turning back because initial velocity and acceleration, they are in same direction. So it starts with a velocity of 2 meters per second and its velocity will keep on increasing. So it is not turning back, it is going in the same direction. So this 16 meters is also the distance traveled. So the answer to the first part, distance traveled, is 16 meters. Second part, time at which velocity becomes 7 meters per second. So this time we are given V, we have to find T. U and A are already given. So you can see first equation connects time to velocity U and A. So we will use equation number 1 for the second part. Let's apply this. V is given, V is equal to U plus AT. So in the position of V, I am putting 7 equal to U is 2 plus acceleration 1 meter per second square times T. So this gives us T equal to 7 minus 5 by 1. So which is 7 minus 2 by 1, which is your 5 seconds. So the time at which velocity is 7 meters per second is your 5 seconds. Now the third part, here we have to find velocity when displacement is 6 meters. So velocity is given, U and A are already known. We have to find displacement. Which equation connects displacement to U, V and A? Here, that's right, it is the equation number 3. So we will use equation number 3 for third part, and we can say V we have to find. So V square as it is equal to U squared, which is 2 square plus 2 into acceleration is 1 and displacement is 6. So it becomes 4 plus 12, which is 16. So V is 4 meter per second. So this is how to decide which equation to use where. I have added 2 more parts to this question. Displacement of particle in the 4th second, and we have to draw VT and ST graphs. So for the 4th part, I will derive a general formula which you can use in such situations later on. Suppose we have to find displacement of particle in nth second. What we can do is, we can find the displacement using this equation in n seconds, and we can subtract the displacement of n minus 1th second. That will give us the displacement in the nth second. Say for example, if we have to find displacement for 4th second, we can find the total displacement of 4 second and we can subtract the displacement of 3 second. That will give us the displacement of particle in the 4th second. So let's do this. Displacement in 4th second. Let me in nth second I am deriving a formula. So let me call this dn. Let me write this as dn. So I can write this dn as displacement in n seconds minus displacement in n minus 1 seconds. This dn represents displacement in the nth second. So this will become, using the second equation, u into n plus half a n square minus u into n minus 1, u multiplied by n minus 1 plus half a n minus 1 squared. And if we subtract this, un minus 1 gives you simply u multiplied by 1 second. plus half a, this we can take common in the second and fourth term, and it is your n square minus n minus 1 squared. N minus 1 squared can be written as n square minus 2n plus 1. So after simplifying, we can get the formula for dn. I will write it here as u multiplied by 1 second plus half a times, it will become n square cancels and it will become 2n minus 1. 2n minus 1 times again 1 second. So this is the result for displacement in nth second. Now for solving the fourth part, you just have to put the values of u, a and n equal to 4 in this result. So it becomes 2 into 1 second plus half acceleration is again 1 multiplied by 2n minus 1, n is 4, so 2 into 4 minus 1, and finally it becomes 2 plus this is 7 by 2, so this is your, you can say 5.5 meters. So this is the displacement in fourth second. Now let's come to the fifth part. We have to draw velocity time and displacement time graphs. See, the velocity time graph, slope of this graph, slope of any graph rather, represents the rate of change or the derivative. In case of velocity time graph, the slope will represent acceleration. Acceleration here is a constant. So it will be a graph with constant slope, which means it will be a straight line graph. So the VT graph will look like this, and of course u is the y-intercept. So the y-intercept is positive and also slope is positive. Basically we are plotting this graph, V versus T. We are basically plotting this graph. You can see V we are taking on the y-axis, time we are taking on the x-axis. You can see it resembles y is equal to mx plus c. So in the place of c we have u, which is 2 meters per second, and the slope is 1. So the graph will look like this. Initial velocity is 2, and then every second the velocity is increasing by 1. So at, you can say t equal to 1 second, velocity will become 3. At t equal to 2 seconds, velocity will become 4, because the acceleration is 1. So for every second traveled, the velocity will increase by 1 meter per second. Now about the displacement time graph, S versus T. Displacement time graph is basically this equation, the second equation of motion, ut plus half at square. This is certainly not a straight line graph, because S is a quadratic function of time. So this is a non-linear graph, it is a curvilinear graph. Secondly, the initial value of S, you can see, is 0. If you put t equal to 0, S is 0. Obviously, for any displacement, you need some time. Alright, so the graph will start from origin, and it is a curvilinear graph, and the graph will look something like this. It will be graph which is swinging upwards because of this positive acceleration. This graph, by the way, we will encounter this type of graphs very frequently in physics. The graphs of such quadratic functions, they are called parabola. So this is a parabolic graph. You will study parabola in great detail in mathematics later on. So for a quadratic function, graph is a parabola. For a linear function, the graph is a straight line. One powered function, the graph is straight line. Two powered or quadratic function, the graph is a parabola. Plotting graphs is a very useful thing. Sometimes we can solve questions using graphs. Particularly VT graph is very important in solving problems. First of all, its slope gives you the acceleration, and secondly, area under VT graph will give you the displacement. So here in this question we can solve at least part 1 and also part 4 using graph. See, it says distance traveled, which we know in this case is equal to displacement in 4 seconds. So let me extend this to 4 seconds. At 4, what will be the velocity? Velocity will again increase by 1. So velocity here will be 6. So this area here is the answer of part 1. You can see this is a trapezium. You can calculate its area. Its area will be what? The sum of parallel sides. 2 plus 6. Half of this multiplied by gap between the parallel sides, which is 4 minus 0, 4 seconds. So this gives you 8 multiplied by 2 equal to 16 meter, which was the answer of first part. And also you can see displacement in 4th second. Now displacement in 4th second means total displacement in 4 seconds minus displacement in 3 seconds. So the answer of 4th part is the area is this area of this thin trapezium. You can see this here is just 1 second, and sum of the two parallel sides will become 5 plus 6 by 2. So half of 5 plus 6 multiplied by the width, which is 1 second. So this gives you 11 by 2 meters, which was indeed the answer of 4th part of the problem. So plotting graphs can also be used for solving some questions. Let's take another interesting example. This is a hot air balloon which is rising up at a constant velocity of 5 meters per second. Person in the balloon drops a stone when its height from ground is 10 meters. The stone drops under gravity, and acceleration due to gravity, we are taking it to be 10 meter per second square. Mind you, the more precise value of G is 9.8 meter per second square, but in most problems of JEE, it is taken as 10 meter per second square just for the sake of easier calculation. So the stone drops with an acceleration of 10 meter per second square downwards. Now for this situation, we have to find these things. Part 1, when will the stone hit the ground? The time when stone hits the ground. What is the velocity at that moment? At the moment of impact, what is the velocity of the stone that we have to find? Maximum height of the stone from ground. Is it 10 or is it something else? Whatever it is that we have to find. And distance traveled till it reaches the ground. So what is the distance traveled till it reaches ground? These are the things that we have to find. So let's start with the first part. Now in this example, we have to be careful about the sign. The sign of vector quantities, as I told you, is decided by their direction in case of one-dimensional motion. So let's take upward as our positive. So it's a motion in vertical direction, so we are taking upward as positive. and I will also mark it here. So I am taking upward direction as positive. So for U, V, A and S, these are our 4 vector quantities. Their signs will be decided according to this notation: upward, positive, and naturally downward, negative. Alright. Now, what is the initial velocity of stone? Question says the person drops the stone. Now, some of you may think that he has dropped the stone, so we should take velocity 0. See, but it is not true. Drops, word drops, it means that the person has not made any effort to change the velocity of stone. So the velocity of stone will remain the same. Whatever it was before being dropped, it will remain same after being dropped. What was the velocity of stone before being dropped? See, stone along with the person, they were being carried by the balloon upwards with a velocity of 5 meters per second. So, initial velocity of stone U is 5 meters per second and it is upward, so it is positive. The second thing is acceleration. Acceleration, you can see, is acceleration due to gravity is downwards. So any vector that is downward is negative. So it is minus 10 meter per second square. So these are our values of U and A. Now let us attempt part 1. Time has been asked when it hits the ground. Now hits the ground means it is 10 meter below its starting position. 10 meter below its starting position. We have taken upward as positive. So what is the value of S here? The value of S we have to take negative and it will be minus 10 meters. So let us put U, V and U, A and S in second equation and solve for T. So it becomes minus 10 is equal to 5t plus half, acceleration is minus 10t squared. Now you can simplify this. In fact, 5 gets cancelled throughout. So it becomes t square minus t and minus 2. I am taking the terms this side. So t square minus t minus 2 equal to 0. Alright. And then you can easily find the roots of this equation. This can be factorized. T squared minus 2t plus t minus 2 equal to 0. And you can get the factors as t minus 2 and t plus 1. Simple maths. Alright. If the equation is, if it is not possible to factorize, then of course you have to use that formula of roots, which is what? Minus b plus minus square root of b square minus 2ac divided by 2a. So it's not needed here. Values are too simple. Now this gives you two solutions for time t equal to 2 seconds and t equal to minus 1 seconds. Now our stone was dropped at the moment t equal to 0. That the moment of initial velocity. So we are not interested in this solution because our motion has started from t equal to 2. Obviously, it will hit the floor after that. So this solution is not relevant to us. So t equal to 2 seconds is the answer of our first part when it hits the ground. Now second part, what is the velocity at that moment? You can use equation number 1 now that we know the time also. So for the second part you can say V is equal to ut. U is 5, u plus 80, a is minus 10 and time is 2 seconds. So it becomes 5 minus 20, that is minus 15 meter per second. We are getting a negative value of for velocity. Is it all right to get a negative value of velocity here? See, the stone is moving downwards when it hits the ground, isn't it? It's quite obvious that stone must be moving downwards when it hits the ground. We have taken upward as positive. So obviously we should get a negative sign for velocity. If we get a positive sign for velocity in this, then we have to be alarmed. Is it something wrong? So this is all right. Negative sign shows that it is going downwards at 15 meter per second at the moment of impact at t equal to 2 seconds. Third part, maximum height from the ground. Now, maximum height, how do we know that the stone has reached its maximum height? What is the special thing that happens at maximum height? See, initial velocity of stone was upwards. At the maximum height, its velocity becomes 0. It is the turning point. Initial velocity is 5 upwards. As it goes up, its speed decreases because acceleration is in the opposite direction. At the highest point, it becomes 0 and then velocity becomes negative as it goes down. So at the turning point of the motion, which is the highest point in this case, velocity is 0. And so we know velocity at this point, u and a are given. Let's calculate s using third equation of motion. So for this part, we will use third equation of motion, v square, which is 0 squared at the highest point of its trajectory. Somewhere here, its speed is 0. So 0 square equal to u square, which is 5 squared, plus 2 into acceleration is minus 10, and s is what we have to find as h max. I am writing it as h. So we can say h is equal to 5 squared, 5 into 5 divided by 2 into 10. So you can see it is 5 by 4 or 1.25 meters. So the maximum height of stone from its, see, this is the height which we have got from the starting point, because this was basically displacement. So from third equation of motion, v square equal to u square plus 2as, v at highest point is 0 squared equal to u is your 5 squared plus 2 times acceleration is minus 10 into s. This gives me s equal to 25 by 20, which is 1.25 meters. So this 1.25 is the height of stone from its starting point. It's not from the ground. This height is 1.25. So from ground it becomes 10 plus 1.25. So the maximum height from ground, h max, is 11.25 meters. So this is the maximum height from ground. Answer of part 3. The stone will initially rise. Reason being, it has some velocity in the upward direction initially. So it will rise up and it will come down. It is not going to hit the balloon anywhere. Don't worry about that, because the balloon itself is moving with a velocity of 5 meters per second, and velocity of balloon is not decreasing. Velocity of stone, by the way, is decreasing. So the balloon will be much higher at the moment when stone reaches its maximum height. So don't worry about the stone hitting the balloon. There is no chance of it. All right. Maximum height is 11.25. Last part. What is the distance traveled till it reaches ground? Now, is distance traveled in this situation equal to the magnitude of displacement? It is a one-dimensional motion. case, all right, but the particle initially goes up to a distance of 1.25, then it turns back, starts falling, and it falls a distance of how much? 11.25 after going up 1.25. So in this case, because the particle is turning, even though it is moving on a straight line, but it is turning at a point and going back, so distance traveled total will be 1.25 upward plus 11.25 downward. So the answer of part 4 becomes 1.25 plus 11.25. So total it becomes 12.5 meters. So in such situations where U and A have opposite signs, we have to be careful while calculating distance traveled. The answer to distance traveled may be different from the magnitude of displacement in such cases. And it will be different in when the duration is such that the turning point is included in that duration. If you had to find the displacement only for a smaller part, only during the upward journey, in that case still you would have got distance and displacement equal, but question says till it reaches ground, so obviously the turning point is included in that, so we are getting distance traveled different from the magnitude of displacement. Magnitude of displacement was in fact 10, distance traveled is 12.5 meters. Let us now look at the same problem graphically. Let's plot these three graphs. First, I will plot acceleration time graph. Acceleration versus time. See, the value of acceleration is a constant. It is minus 10 meter per second square. So, the graph will have zero slope. It's not changing. Acceleration is not changing. Its value is simply minus 10. So the graph will look like this. Acceleration is minus 10 always. Now the velocity time graph. V t. Initial velocity is 5 meter per second, maybe somewhere here. But then it is decreasing. So this graph will have a negative slope. So it may look somewhat like this. Where will the velocity be zero? See, the velocity was zero at the highest point, isn't it? How much time will it take to that zero velocity? See, the slope of this graph is minus 2, or acceleration is, minus 10. So, it will just take how much? Half second. You can use the first equation of motion. V is your 0, U is how much? 5, acceleration is minus 10. That will give you t equal to half second. So, this is, you can say 0.5 second where its velocity is 0, and then it is going down. So this is the point, this point here of the graph where velocity is 0 refers to the highest point, this point here. Alright, so the time here is half second, and then it is going downwards at a constant acceleration. The graph will remain the same. See, even if the journey has changed, even if the direction of motion has changed from upward to downwards, it is the same graph. It is one motion. Acceleration has not changed. So we don't have to consider the upward journey and downward journey separately at all. It's the same graph that is continuing here. We can put one more point that we know of. The velocity when it hits the ground at t equal to 2 seconds, and the velocity at that point was how much? We got it as minus 15. So that point also we can put on this graph. Now the third graph. Third one was ST graph, or the displacement time graph. ST T graph here. Now in this graph, at t equal to 0, displacement is 0. 0.5 second, the same point refers to the highest point of the graph. So the value of S will be maximum positive at t equal to 0.5. So, and the graph we know is a parabolic graph. The quadratic function give you a curvilinear parabolic graph. So this graph will look somewhat like this. It will be like this. At 0.5 seconds, it is at maximum height, which we calculated as 1.25 meters. So at this point, at 0.5, its value of S will be 1.25 meters. Alright, this is S versus T. Now, when there is a point where its displacement is 0, and it is not t equal to 0, after some time its displacement is 0. If you want, you can calculate it from here, that at what time it comes back to the starting point. You can put S equal to 0 and you can solve. You will obviously, one solution is t equal to 0. The other solution you can see easily is going to be 1 second. You can see it from graph. You can see this solution graphically also. You can see this point of returning at the same instant of same position from where it was dropped. You can see that from this graph also, VT graph. See, we know that area under VT graph gives us displacement. Now, this part of the graph is positive displacement because it is above the x-axis. Here it is your time axis. So the area which is below the time axis will be your negative displacement. So after how much time will this positive displacement be compensated with the negative displacement? You can see that these are similar triangles. Alright, similar triangles, and we want their areas to be of equal magnitude. So obviously this time from here, from the point, from the instant when it is at highest point to the point when it reaches back the same point, will be same duration of 0.5 seconds. So in all it becomes 1 second. At 1 second, this point corresponds to this one here, where displacement is 0. Positive displacement compensated by negative displacement. Here it is at t equal to 1 second. Alright. Now of course we can plot this 2 second point also, because we have done the calculation. At t equal to 2 seconds, the particle had hit the ground. So the value of S here should be minus 10 meters. Alright, we have already done the calculation for this. You can see the maximum height from VT graph, and you can relate it to the ST graph. The point when it comes back to the starting point, again they can be related from VT and ST graph. What about the distance traveled? How to get distance traveled from let us say VT graph and ST graph? From the VT graph, we can get distance traveled by adding area of this triangle and this area of this triangle. If we want to get the total displacement of 2 seconds till it hits the ground, we have to add both these areas, not subtract. Because distance traveled is never negative. Distance traveled can only increase. Distance traveled cannot decrease. Alright. Well, when it was going up, it was traveling distance. When it comes down, it is still traveling distance. So distance traveled only adds up. So if you add the areas of these two triangles, you should get 12.5 meter. You can try doing this calculations. Graphs are there in front of you. How to get distance from this ST graph? See, you have to look at the graph completely. First, it is going up from 0 to 1.5. So that 1.25. So that is a positive distance traveled for 0 to 0.5 seconds. And after that, it it comes down a distance of 11.25. So you have to add 1.25 and 11.25 to get total distance traveled from this graph. One more thing, how to relate acceleration time graph with the, let us say, velocity. See, area under AT graph, what will this give? See, area under AT graph, we know area in general means, acceleration, sorry, in general means dv by dt. So, dv integral will give you a dt integral. This is area under acceleration time graph. I am taking a general case. Even when acceleration is not constant, you can find this area using, you can find this integral by area under the graph. Alright, and you will of course put some limits, let us say initial limit 0 to some time t1 and initial velocity u to v. So left hand side, what it becomes? It becomes change in velocity. So area under the acceleration time graph gives you change in velocity. You can check it here also. Let us say if I take a time from 0 to 0.5 seconds. Alright, 0.5 seconds. What is the change in velocity? What is the area under AT graph? You can see 0.5 times minus 10, it is 5 meter per second. So 5 meter, because this is, see, unit of area, you can also see this is 10 meter per second square. So this multiplied by 0.5 seconds, this will become minus 5 meter per second. So that is the change in velocity for this duration of 0.5 seconds. And you can see velocity initially was 5 meter per second. From here it drops to 0. So change in velocity is 0 minus 5, that is negative 5, given by the area under the graph. You can check it for other durations also. Total, let's say from 0 to 1, if we take this total area, this 1 multiplied by minus 10. So change in velocity for 1 second should be minus 10 meter per second. And you can see the velocity, which was 5 meter per second here, at t equal to 1 second, it becomes minus 5. You can see it in this graph, or you can calculate from this equation v is equal to u plus at. And at this time t equal to 2 seconds, when it hits the ground, again for total, this total area is how much? It becomes 20. So change in velocity for this duration of 2 seconds is your minus 20. Alright, and you can see what is happening. It changes from plus 5 meter per second at the starting point to minus 15. So the change is minus 20 meters per second in the velocity. This was meter per second. Alright, so these graphs are related. This AT graph gives you change in velocity. Area under AT graph gives you change in velocity. Area under VT graph gives you displacement. And the slope of ST graph gives you the velocity. Alright, you can check it here. At the highest point, this is becoming horizontal. So the slope is 0, which refers to 0 velocity. So slope of ST graph gives you velocity. Slope of VT graph will give you acceleration. See, the slope of this graph is a constant, negative. In fact, it is minus 10, which is given here. So this is how these graphs are related to each other. See, in physics, such questions, there are in fact, you can say 3 different ways of expressing yourself, 3 different languages. One is the language of, you can say, diagram and the written words, which is usually the language of the question. It's written in words and some diagram may be there. So that is one way of communicating. Second method is in terms of equations and calculations. Alright, and the third language that is used in physics is the language of graphs. So a skill that you need for mastering physics is to be a good translator, to translate the language of question and diagram into equations, and to translate equations into graphs, and the other way around. So if you can master that skill, it will help you a great deal in solving not just kinematics, the problems of entire physics.